Here we prove that if we do row operation of type 1, meaning that two rows of the matrix are interchanged, then here's the result. Interchange two rows, change the sign of the determinant. So plus become minus, minus become plus, and that's all. Just change the sign of the determinant. And here's the way we prove it. We prove it by induction. The induction for n, right? N is the sign of the matrix A, n by n. N greater than or equal to, right? That's why we can have the two rows, only two rows to interchange the rows. So the base case is for 2 by 2 matrices. A is an A 2 by 2 matrix, and we exchange two rows of A, become A11, A12, A21, A22, become this matrix. Change the first to the second and the second to the first one, the first row to the second row, and the other way around. Then for 2 by 2 matrix, we can just verify the determinant of the new one. This determinant, after we exchange the two rows, then this determinant equal to A21 times A12 minus A22 times A11. That is, by definition, we know that this is minus determinant of A. So multiple E, see, is a matrix correspond to exchange two rows of A, then equal to the determinant of E, which is minus 1 times determinant of A, equal to minus determinant of A. So this is true for base case 2 by 2 matrix. Right. For 2 by 2 matrices, if we exchange two rows, the determinant change the sign. Now we need to prove it for n greater than 2 or n greater than or equal to 3. Let now denote Eij, the elementary matrix, correspond to the row operation of type 1. Thus we switch row I and row j of the matrix A. And here's what we will prove. Determinant of Eij times A equal to minus determinant of A. This matrix is, in fact, it is just the resulting matrix after we switch two rows, row A and row I and row j of matrix A. Here's the idea for n equal to 3. Now we have 3 by 3 matrix. If we exchange two rows, row 1 and row 3, and here's the matrix, resulting matrix. Row 1 become row 3 and row 3 become row 1. Row 2 we keep the same. Now what do? We will use the definition of determinant. We do cofactor expansion over second rows. The rows that do not change when we do the row operation of type 1. We only exchange the first and the third row, so the second row keep the same, right? We will do cofactor expansion over that rows. So the cofactor expansion over second rows is A21 times big A21, right? A21 times minus 1, 2 plus 1, right? So that's minus 1 A21 times, deleting this row and this column, times this matrix with this 4 and 3, right? A32, A33, A11, A13. Similarly, we do the same. A22 times minus 1, 2 plus 2, so it's plus 1. Determinant of the matrix after we delete this row, this column. A31, A33, A11, A13. And the same. Minus A23, because A23 times minus 1, 2 plus 3 times the determinant of this matrix. So these 4 and 3. These 4 and 3. And now we can use what we did before for 2 by 2 matrices. So these are 2 by 2 matrices. And we know that if we switch 2 rows, then the determinant change the sign. Now that's what we do. We switch 2 rows of this matrix. The matrix we get is the row 2 become row 1 now. The row 1 become row 2 now. And this one we exchange 2 rows, change the sign. Now minus become plus. A2, 1 keep the same. We do the same thing, exchange 2 rows of this matrix, becomes this matrix, and because of doing so, because of what we did, we showed before for 2 by 2 matrix, if we exchange 2 rows, then the determinant change the sign, plus now become minus. The same thing happened here, we exchange 2 rows for the 2 by 2 matrix, the determinant change the sign, minus become plus. And here, by definition, by cofactor expansion over second rows of matrix A, the original matrix, this one is in fact minus the determinant of A. I repeat, this is because determinant of A equal to minus of this quantity. This is cofactor expansion over the second rows. Because everything here just A21 times minus big A21, right? Big A21 is a cofactor expansion over second rows of A. The same thing. So this is, we have determinant of E13A equal to minus determinant of A. So if we exchange 2 rows for 3 by 3 matrices, then the determinant change the sign. And that is the idea when we do it for n equal to 3. And the proof will be exactly the same for big N, bigger N. So here is a proof by induction. We start with the first step, base case. So Pn is a statement with variable n. So the statement is if or let A be an n by n matrix and greater than or equal to determinant of Eija equal to minus determinant of A. Here Eij is elementary matrices correspond to the row operation that we switch row I and row J. Base case n equal to, so P2 is true. This we verified before, right? We just verified at the beginning. Now inductive step, suppose that Pn is true. We will show that Pn plus 1 is also true. What does that mean? So suppose that this is true. We will show that Pn plus 1 is true. We will show that if A is an n plus 1 by n plus 1 matrix, now we show it for n plus 1. Then the determinant of this Eij times A is equal to minus determinant of A. So we can still switch 2 rows of the new matrix, the matrix A that of the side, just one side bigger than n by n plus 1 times n plus 1. So remember what we did for the case n equal to 3. We do cofactor expansion over the rows that do not change, right? So we can do cofactor expansion over row K, where K is not or does not belong to the set I, J. So K is different from I and K is different from J. And we do cofactor expansion over the row K of this matrix. And we call this matrix A star. So it's AK1 times A star K1 plus until AKN times A star KN. And we know that A star K1, okay, let's look at this cofactor. So A star K1 is, in fact this is minus 1 K plus 1 determinant of the matrix MK1 star, right? MK1 star is an n by n matrix. MK1 star, what is this matrix? This is a matrix A star deleting row K column 1, right? So this is an n by n matrix, And by inductive hypothesis, so Pn is true, right? Because it is true for all n by n matrix. So it's true for mk1 star, which is an n by n matrix. Then this determinant will be minus determinant mk1, where mk1 is a matrix that we split two rows, row I and row j of A star. And what is this? This value is in fact, this value, so I put minus 1 here and minus 1k plus 1 determinant mk1. So this quantity is in fact the cofactor of ak1, right? The cofactor of ak1, and this is minus ak1. Similarly, we'll do the same thing for a k2 star, a k3 star, and a kn star. At the end, we have determinant of the new matrix, the matrix after we switch row I and row j of A. This is equal to, this one is what we have by doing cofactor expansion over row k, right? And here, after we switch, we use the inductive hypothesis, we switch two rows I and j of this matrix, we get this cofactor ak1, cofactor of a small ak1 in the matrix A. This one is in fact minus the determinant A, where this is true because this quantity is minus cofactor expansion of matrix A over row K, and therefore Pn plus 1 is true. We did prove that Pn plus 1 is true using the inductive hypothesis. Therefore Pn is true for all n greater than equal to. At the end, what we need to remember here is that if we exchange two rows of a matrix, the determinant change the sign.